Okay, so now that we've defined momentum, we've defined impulse, we are ready to prove a very useful theorem. It's called the conservation of linear momentum theorem. Now, this is very similar to the other conservation theorem that we learned about mechanical energy. Now, conservation once again means that the linear momentum will not change. So what the theorem says is that if the external force on a system is 0, then Pi equals Pf. Which means what it says is that if there is a system which could be more than one object, and it's easier to deal with more than one object. For one object, it's very trivial. If there is one object and if you have no forces acting on this object, then the momentum is not going to change. So it's very trivial. However, if you have more than one object, it may not be as trivial. So if you have two objects or more within a system, and if the net external forces, net external force on the entire system is 0, then the initial momentum is equal to the final momentum. Okay, it's a very powerful theorem. It can be applied to many things, and it leads to learning about collision. So let's prove this first, and the proof is actually very easy. We're going to use the definition of our impulse momentum theorem. Okay, from the impulse momentum theorem, what we know is that F times delta T is equal to Pf minus Pi. Now here F is the force acting on a system, and so if F is equal to 0, then Pf minus Pi equals 0. Now, which clearly implies that Pi is equal to Pf. So this is our theorem. It says that the net external force on a system is 0, then the momentum, the linear momentum of the system will be conserved. So if F external is equal to 0, then the linear momentum of a system will be conserved. So the momentum that we've studied so far, okay, the P, and I know that I didn't really specify this, it's all linear momentum. So if the net external force is 0, the linear momentum of the system will be conserved. So let's apply this to a simple situation first, and then we'll look at some more interesting ones. Okay, so let's say that there are two people standing on ice. This is one person, and let's say there are two people here facing each other on ice, and let's say they have really long arms, which is a prerequisite for these things. And let's say they're standing next to each other. The mass of the first person, let's say, is capital M. The mass of the little one is lowercase m, and they're both at rest. Okay, they're standing on ice, which means there is no friction. Okay, so ice, which would mean saying there's no friction, so mu equal to 0. And what's happening is they're pushing each other off. And what is observed is that the big guy moves to the left with a speed of v. And the question is, with what speed does the little guy move? And what direction is the person moving? So we will use the conservation of linear momentum to address this problem, and the reason we can use it is because the net external force is 0. Now you may ask, hey, but they are pushing each other off, and if they are doing that, okay, how come the net external force is 0? The answer to that is very simple. When they're pushing each other off, the push is happening right here at the contact. So the push, the left guy is pushing the right guy to the right, and the right guy is pushing him back to the left. So this force here is an action-reaction pair, and they simply cancel each other out. And if you notice, the net external force, I mean, of course, there's gravity and contact, but they cancel each other out as well. And since there is no friction, there are no outside forces on the system. And so now we can use the linear momentum conservation theorem. Okay, so use Pi equals Pf. Now, since we have two things, okay, we can, when we write the momentum, we need to account for the momentum of each individual. So in the beginning, the momentum of the big guy is 0. The momentum of the little guy is also 0. And in the end, the momentum of the big guy is m times v, but it is negative because it's moving to the left. So again, keep track of the directions. And the momentum of the little guy is m times some v final. Okay, the v final is what we're looking for. So now what we have is 0 is equal to lowercase m v final minus capital M times v. And now I can simply write it as m times v final equals capital M times v. And so v final is equal to capital M times v over lowercase m. Now, it's a simple situation now here. Okay, you notice that since capital M is greater than lowercase m, okay, this velocity, the speed of the lower mass object is going to be higher. So when you have these collisions, okay, now this could be, instead of two people, you could have a situation where a gun is shooting a bullet. And if the gun is shooting a bullet, then what you'll have is that the bullet and the gun will have the same momentum. Okay, if they started, say, at rest, they will both have the same momentum. And then after the bullet is shot, the bullet's velocity will be, the mass of the gun divided by the mass of the bullet, which will be a large number, multiplied by the velocity of the gun. And you see that will end up making sure that the velocity of the bullet is higher than the velocity of the gun. Okay, so in this problem, what we did is we simply found the change in the velocity of the person at the end. Now, what another thing we can also do is find the change in the kinetic energy of the system. Okay, so the delta KE for the entire system will be equal to KE final minus KE initial. Now, obviously, in the beginning, since nothing is moving, the initial kinetic energy is 0. So we just have the final kinetic to deal with. So the final kinetic will be the mass mv square for the big guy plus 1/2 times m times the small one's velocity minus 0 because they're both 0 in the beginning. And you can simplify this and you can get 1/2 times m times v square plus 1/2 times capital M square over m times v square. And this becomes, I can take the half out, I can take one of the m's out, and also the v square out, and what we are left with is 1 plus capital M over m inside the radical. So this is the total change in the kinetic energy. And of course you can ask, where did all this energy come from? And this comes from the push. Like, the two guys had to do some work, and that work is what got converted into energy. Okay, so thus giving each one of them some amount of kinetic energy. Now in a gun bullet system, this energy would come from the explosion inside the gun, the chemical reaction that propels the bullet in the forward direction. Okay, so the same concept can be used provided everything starts at rest. All right, so that's a simple application of the not just the application, but we looked at the conservation of linear momentum, and then we applied it to a simple situation.